Hey guys, welcome to Master and Learn It. In the previous video, we have proved cos A minus B equals to cos A times cos B plus sine A dot sine B. Hence the need, it's on the red ink to say that we have already proved it in the previous videos using the Cartesian plane. But the rest of these other compound angles can be proved just using the connection of the cosine compound angles. So let us start deriving. So let's derive. How can we derive cos A plus B using this? So we know that cos A plus cos B can be written using this as, so I'm going to write that using this connection is the same as cos A minus negative B. So are these things exactly the same? Yes, they are, because we have cos, that's cos, A, that's A, and negative times a negative, that's a positive. So that's exactly the same. So you should be able to understand that negative angles, this is the prerequisite information you should know before you attempt to prove this. We should know that a negative angle, especially if it's a negative small angle, it means the angle, all negative angles are measured clockwise. So we all measure angles from the positive x-axis. So a negative angle means we measured a small angle clockwise and it ended in the fourth quadrant. And we know that in the fourth quadrant, cos is positive. That's why we have cos negative theta equals to positive cos theta. But should you measure sine from the positive x-axis and you measure clockwise, we get an angle of theta which is in the fourth quadrant, and we know that sine is negative. That means sine negative theta, negative showing that it was measured clockwise, we get negative sine theta. So this is something that you should be able to understand. So now we have written a connection of cos A plus B in terms of this. So now we can expand that. We know that this can be written as cos A times cos, and our B being negative B time, that means we have plus sine A times sine, and our B being negative B. This simplifies to cos A times cos B is a negative theta. That means it's an angle that was measured from the positive x-axis clockwise, so it's in the fourth quadrant and cos is positive, so this is cos positive cos B. Then we should know that sine A, that's positive, but negative sine B, it means it's an angle in the fourth quadrant, and we know that sine is negative in the fourth quadrant. So that negative is going to affect this one, so I'm going to write it in a different color. That becomes negative, that's coming from the sine angle, which is sine A times sine B, the negative showing us the direction. So we've derived that cos A plus B equals to cos A times cos B minus sine A dot sine B, which is exactly what we have right there. So this is how we derive. So this is how we derive, that's the derivation of cos A plus B. So we just created a connection of the first compound angle we have formulated already. How do we prove sine A plus B? So sine A plus B can be also written using cos of this, but we should know the connection between cofunction angles. This is very, very important. We know that cos 90 minus a theta, we get sine theta. Sine 90 minus theta, we get cos theta. So that's the same way that I'm going to write sine in terms of cos. So this one I can write it as cos 90 minus A. So that's cos 90 minus, then we have our theta being A plus B. Isn't it? This is the same, because cos 90 minus an angle, we get sine of that angle. So cos 90 minus this angle, we get sine of that angle. So these are exactly the same. And mind you that we've created also the same connection where we have an angle, that's an angle, there's a minus, then there's a minus, and there's an angle there. So from there we can clear brackets, so this simplifies to cos, that simplifies to cos 90, and negative times a positive, we have negative a, and negative times this we get negative b. So this one can now be written explicitly as cos 90 minus a, so this is an angle on its own, minus b. So we should know that this b doesn't mean it's a negative. This negative is this default negative. 90 minus a represents this angle, and this minus represents that, and this b just represents the b. So we can now apply exactly as it is to say this can now be written as cos 90 minus a times cos b, then we have plus, so I'm going to write in a different color, sine 90 minus a dot sine b. Then this simplifies to cos 90 minus an angle, not cos 90 minus an angle, we get sine of that angle. So this simplifies to sine a times cos b plus sine a minus theta, that's sine 90 minus a small angle, get cos of that angle, so that becomes cos a times sine b. So which is sine a plus b can be written as sine a times cos b plus cos a times sine b. So we have derived sine a plus b. How do we derive sine a minus b? So we're gonna just show it right here. So derivation of that is sine a minus b can be written also in terms of cos as cos 90 minus, then we have our angle being a minus b. Then this can simplify to cos 90 minus a, and negative times a negative we get positive b. Right, so this now we can rewrite this one as cos 90 minus a plus b. And what do we notice? This is cos angle plus another angle, which is cos angle plus another angle. So now I can use this compound angle of cosine. So now we can come and say this can simplify to cos 90 minus a times cos b. Then we have, remember when we are dealing with a plus there, it becomes a minus. So since we are dealing with the plus, then we put a minus. Then we have sine 90 minus a times sine b. And this simplifies to cos 90 minus a. You now know that this can be written as sine a times cos b minus, then sine 90 minus a can be written as cos a times sine b, which is simplifies to say, so therefore sine a minus b is equal to sine a times cos b minus cos a times sine b, which comes to that. So this is how we prove the compound angles. So a little bit of practice is going to make these ones pretty much more simple. Thank you, and see you in the next video.